Well, thank you for the lovely introduction. In this talk, I'll present an elementary framework for orbit counting, which has the advantage that it requires only the minimal regularity hypothesis on the dynamical system. In this talk, for concreteness, I'll focus on rational maps, but the ideas are valid for general conformal dynamical systems. So let F be a rational map acting on its Julia set. So at its simplest, orbit counting is concerned with counting repeated preimages of a point X on the Julia set. So points Y, which iterate to X in some number of steps. So I call this a repeated preimage. One can also count other things like periodic orbits or, say, complementary components of size at least delta. But those questions are generally reducible to counting preimages. So if you can count preimages and you're lucky, you can also count other things. So what we do is we look at this counting function. So we count the number of preimages Y, which map to X in some number of steps with a bound on the derivative. So this is a central object of this talk. So to state the orbit counting theorem, we are forced to make two assumptions on the rational map. So the first assumption asks that the Julia set carries a conformal measure of dimension alpha, where alpha is some positive number. So this means that F prime to the alpha qualifies as the measure theoretic Jacobian of F, of M. More precisely, one asks the measure of F of E is given by this formula, provided that F is injective on E. Our second assumption is that the Julia set also carries an absolutely continuous invariant probability measure, which we call mu. And we ask that the Lyapunov exponent is positive. So the Lyapunov exponent measures the average rate of expansion along forward orbits. So we make those two assumptions on the rational map. So we say that the orbit counting theorem holds for a rational map F if NXT has the following asymptotics. Gamma is the Radon-Nikodym derivative. So just looking at this formula, it involves alpha, it involves mu, it involves M through gamma, and also the Lyapunov exponent needs to be finite for this formula to make sense. So in order to state this theorem, one is forced to make those two assumptions. The two assumptions are necessary to even get started.
Can you give some sufficient conditions on the rational map?
Yes, you'll see in a second. So here's the main theorem of this talk. It's very simple and it's presented on like the second slide. So the orbit counting theorem holds for all rational maps satisfying the two axioms with a small set of exceptions. And we'll see the exceptions on the next slide. So in other words, the orbit counting theorem holds whenever you can, whenever it makes sense. Here are some classes of maps which satisfy the axioms. So first, by the work of Juan Rivera Letelier and Felix Pshitsky, the above axioms are satisfied for so-called topological colored Ekman maps. And in this case, the alpha is equal to the Hausdorff dimension of the Julia set. Another class of maps has been defined by Grachik and Smirnov. The two classes have a large overlap, but one isn't contained in the other. So they are different classes. And in fact, there have been further work on this. So T, yes, so T is this cutoff on the derivative. So n can be arbitrary. We do not fix n. So this is the main theorem. Yes. No. I think there is some uniqueness, but I'm not an expert. But I think no. I should also mention that this theorem is also valid for some parabolic maps like the cauliflower. So those assumptions forbid parabolic points, but parabolic points aren't really bad. So here are the exceptions. A map is called exceptional if it looks like a power map, a Chebyshev polynomial, or a lattice map. So, for example, in case of z goes to z squared, the Julia set is a circle. And the derivative is always a power of 2. Yes, no, left, right. So for the z goes to z squared, one expects that the number of pre-images looks like e to the power of floor of t rather than e to the t. And the same thing holds for the other exceptions. So my point of view is that the exceptions do not exist. I do not think of lattice maps. So don't ask me what they are. They don't exist for me. More generally, one can study orbit counting with rotation. So given an arc on the circle, one can count repeated pre-images where the argument of the derivative belongs to I. And one expects that for a generic rational map, the argument gets equidistributed in the circle. So, and the answer is the orbit counting theorem with rotation holds for every rational map, but this time we have a larger list of exceptions. We also need to exclude the rational maps whose Julia sets are contained in a circle or a line. So, for example, if the Julia set is contained in the real line, the derivative is always a real number. So one has to exclude those examples, but otherwise you're fine. So this is the second main theorem of this talk. So as an aside, for comparative purposes, let me mention an application to one-dimensional dynamics. And this concerns so-called Adler maps of the circle. So the definition is not important, but I'll mention that the Gauss continued fraction map is an Adler map, and it's an example which sort of motivates the general definition. So if you are looking at derivatives and you're not sure what those things mean, don't worry. But the theorem says that the orbit counting theorem holds for any infinite to one Adler map such that the Lyapunov exponent is finite. And this condition is absolutely necessary. So this is just for comparison purposes.
What is that?
M is some number. M could be anything.
No, DM, the measure.
Oh, M is the conformal measure. So maybe I should have written mu, but in this case, M and mu are equivalent. The Radon-Nikodym derivative is bounded above and below. So M is actually just a big measure on the circle. So let me give some history, and I apologize that my history is going to be incomplete. But I'm just describing the history which personally influenced me. So in 1989, Stephen Lally introduced a general framework for studying orbit counting problems. And his approach has three pillars: thermodynamic formalism, Poincare series, also known as zeta functions, and Tauberian theorems. And I want to emphasize that this framework works for very special dynamical systems, namely hyperbolic ones. So if you're not sure what hyperbolic means, I'm going to define it later, but for now, hyperbolic just means simple. Also, it means done to death. So in 2017, Mark Polikot and Mariusz Urbanski wrote a book, maybe 140 pages. This is typical of Mariusz, where they extended Lally's approach to countable Markov shifts. But the main drawback of this approach is that they require that the zeta function has a meromorphic extension to a slightly larger half-plane. So in the context of Adler maps, one doesn't get this condition, one gets this condition. In 2023, Mariusz Urbanski and I used a slightly better Tauberian theorem. And with this approach, we got it down to this condition. So as you could see, there is an epsilon here. So no, but but they still need this. They still make such an assumption.
Yeah, but they don't. Yeah, they need this assumption, but they didn't extend the data function to a slightly larger argument. They extend the data function across the critical line. That's enough.
Yes.
That have to be a larger argument. But if they did extend it to a larger argument, then they would have to.
No, they wouldn't have, because they are not familiar with the Dolgopyat machinery. I'll mention this in a second. Well, he knows of it, but the machinery is very complicated. So it's not that they didn't want to do the work. So I'll mention you in a second. So in dynamical systems, mathematicians don't care about epsilons. But I am an analyst, and epsilons keep me up at night. So using this framework, we get the optimal result. So we get without the epsilon. So now here's some more history. In 2017, O and Ginter proved the orbit counting theorem with rotation, with an additional error term, but only for very special regular dynamical systems. Quite recently, Lee and Rivera-Letelier extended the O-Ginter result to TCE rational maps, which could be quite irregular. So this is truly a fantastic result. This relies on the meromorphic extension and on the Dolgopyat machinery, which is very technical, and Lee is an expert. So here's some more history. And now we're going to travel back in time to 1997, when Misha Lubitsch and Yair Minsky introduced affine and hyperbolic laminations not defined to rational maps. So in some sense, the hyperbolic lamination functions as a hyperbolic filling of the rational map. A similar notion is the barycentric extension of the rational map to hyperbolic 3 space. So originally, when I thought about this project, I was thinking about those objects, but it turns out that it's not necessary for reasons. Okay. So in 2010, Alexei Glutsuk showed that if F is convex co-compact, which means that it's critically non-recurrent and there are no parabolics, then holospheres are dense in the hyperbolic lamination. And from this, he deduced the unique ergodicity of the holospherical flow. I'm not going to explain this. It's technical. I want to give a fun talk. And it's not going to be relevant to my presentation anyway. But the thing I want to focus on is on unique ergodicity. So the reason Glutsuk makes a very strong, relatively strong assumption on the rational map is because he wants to prove unique ergodicity. This is what he is after. And unique ergodicity is a very strong assumption. So it says something about the behavior of every orbit. While in this talk, for orbit counting, we need mixing, which is a lot weaker because it is about the behavior along almost every orbit. So basically, for rough rational maps, those objects, when properly defined, have many special leaves. And for unique ergodicity, those leaves play an important role. But in this talk, all those leaves have measure 0. So we really don't need to worry about this. So I'm just trying to explain why Glutzuk makes this very strong assumption and we make no assumption. And finally, we travel back in time to the work of Bedford, Fisher, and Urbanski, who studied the scenery flow for hyperbolic Julia sets. So the scenery flow has to do with something when you take a point in the Julia set, start zooming in and seeing how it looks like in the Hausdorff topology. And they showed that this scenery flow, not defined, was ergodic. So in this talk, we prove a very strong generalization of this fact here. And now we come to my motivation for studying orbit counting of rational maps. So in 2024, Mariusz Urbanski and I studied orbit counting for inner functions. And we proved ergodicity of the geodesic flow. And this led to showing the orbit counting theorem up to a Cesaro average. So up to some additional averaging, which I will not describe. And we have a partial result for the general orbit counting theorem. So I asked Mariusz whether one can use the same set of ideas verbatim to handle rational maps. So it turns out that the two works, so it turns out that the two works are orthogonal and have different sets of challenges. So in some ways, inner functions are simpler than general rational maps because they are uniformly hyperbolic. But in some ways, inner functions are harder because the Riemann surface lamination cannot be expressed as, or cannot be always expressed as a suspension flow over the solenoid. So while the two works have some intersection, they are different works. So it's not that I'm doing the same thing twice. Other questions? So this is the history. Now, I want to define the main object of my work. So to do this, we take a dynamical system, F, and suppose it has an invariant measure, mu. So we form the so-called natural extension. Namely, we define a new space, x hat, which consists of all backward orbits under F. The map F hat acts on x hat by applying F to each coordinate. In other words, F hat is just a shift map. And finally, one can construct a natural measure mu hat on x hat, which is F hat invariant and projects to mu on each coordinate. So basically, the natural extension is the simplest dynamical system which makes F invertible. So this definition is quite well known in dynamical systems. So the next step is to take a suspension flow over x hat. So we use this roof function. And what we do is we first take the product of x hat with the positive real numbers and quotient it out by this equivalence relation. On the suspension space, we have a suspension flow which acts on the t variable. And we also can construct a natural measure mu hat rho on the suspension space. So the main object of this talk is the space x hat rho. So I gave the definition, but you could forget it if you really want to. So in some sense, x hat rho is a hyperbolic filling of F. And I'm using this word on purpose because Aaron knows what I'm talking about. So maybe I'll draw a picture in case you're not familiar with suspensions. So we have this roof function. And the suspension flow moves up until we hit the upper side, and then we teleport to the point f hat x1. So this construction is very well known in dynamical systems. Finally, I want to mention the following simple observation is that if the Lyapunov exponent of F is a finite number, then this magical measure happens to be a finite measure. And this allows us to do ergodic theory. So I don't believe in infinite ergodic theory. And here are the two theorems. First, if the suspension flow is ergodic, and this theorem is stated in a stupid way because this assumption is actually always satisfied, then F satisfies the orbit counting theorem up to a Cesaro average. And the second result says that if the suspension flow is mixing, then F satisfies the full orbit counting theorem. So if you're wondering why I'm talking about mixing of certain flows and not orbit counting, it's because of this theorem. So we are really interested in the mixing of a certain flow. Now, in the context of non-uniform hyperbolicity, which I will define, the suspension flow is mixing if and only if a certain functional equation, this one, has no non-trivial solutions. So you don't have to memorize this. Hello? So from what I have told you, my work has at least three main objectives. And in fact, it has a hidden secret objective, which I'll mention at the end. This is where Neil Dobbs is going to come in. So the first step is to go from mixing to orbit counting. And this uses McMullen's theory of almost invariant functions. The second objective is to say that if you don't have eigenfunctions, if the function equation has no non-trivial solutions, to get mixing, we use an argument due to Martin-Babillot. And finally, the third step, to go from the existence of eigenfunctions to the rational map being exceptional. We use the work of Walker-Meyer. So the first rigidity theorem of this type was proved by Anna Zdunik, and there was a follow-up paper by Fisher and Urbanski. While I have learned a lot from those works and incorporated some of their ideas into my research, I found the work of Walker-Meyer more accessible. So I couldn't just use Zdunik's work as a black box. I had to slightly reach into this black box. Not much, but enough that I had to understand what was going on. And Walker-Meyer's work was really quite accessible to me. Now, if one wants to go and prove orbit counting with rotation, one has to combine Walker-Meyer's result with a rigidity theorem of Yeremenko and Van Steen. You know this is a great result judging by the authors. So the theorem I used is the following. Suppose a relatively open subset of the Julia set is contained in a smooth arc. So not just a subset, but a relatively open one. In this case, the Julia set lies in a circle or a line. Truly remarkable result, and the proof is just brilliant, which is to be expected. So this is the general strategy. Now I want to say something about non-uniform hyperbolicity because it plays an essential role in this work. So let's say this is the Julia set. When I draw a Julia set, I draw a Jordan curve, even though Julia sets are typically not Jordan curves. And suppose you have an inverse orbit. We say that the dynamics of F is univalent asymptotically linear, or UAL, along this inverse orbit if there exists a ball centered at x0 of some radius, so that the inverse branches of F are well defined on this ball. So we can invert F along this inverse orbit forever. But there are two more conditions. We also want the diameters of the pre-images to shrink. And finally, we want F to be more and more linear when we iterate backwards. So we want F to be asymptotically linear. And linear enough so that we can extract a rescaling limit from the inverse iterates. So those the sequence of maps has some rescaling limit, which I use this notation. I'm just happy I could put something to power minus infinity. So some people may be upset at this notation, but I love it. So now we come to a very familiar definition. We say that the dynamical system is uniformly hyperbolic if the dynamics is UAL along every inverse orbit, and the radius R, the radius of this ball, can be chosen to be independent of the inverse orbit. So this is a very standard definition. Now, suppose X carries a natural measure, mu. In this case, we can weaken this definition and say that F is non-uniformly hyperbolic if backward iteration is UAL for almost every orbit. And this time, the radius can vary with X. So this widens the class of hyperbolic dynamical systems considerably. So now we come to 1984, when George Orwell's book was taking place in reality. At this time, Ledra-Pié proved the following result. Suppose F is a rational map, and suppose it carries an invariant measure with a positive Lyapunov exponent. Under those very minimal assumptions, F is non-uniformly hyperbolic. So this is like you don't need much to have this. So this result was also written up by Przyczki and Urbansky in their famous book, Conformal Fractals. When I was trying to understand the proofs, I came up with the following statement. So let me define this quantity, delta F XR. So this quantity, delta F, is the linear distortion of F near X at scale R. And it measures how far away F is from being a linear map in the ball centered at X of radius R. What this theorem says is that if the total linear distortion at small scales is finite, then you have non-uniform hyperbolicity. So for rational maps, they have finely many critical values. Rational maps are very simple. And so one recovers Ledra-Pié's theorem. One can also apply this to transcendental dynamics. But in this case, things are more complicated because transcendental maps can have infinitely many critical values, and a capital delta may not be finite. For applications, see the work of Anna Hover. So this is my understanding of Ledger-Pierre's theorem. I think my proof is a bit simpler than the proofs in the other sources. Okay. So to conclude, let me mention a very beautiful result, a very fundamental result by Martin Babillot. And this is very general. So if you didn't like my talk, you should pay attention here. So suppose you have a metric space, any metric space, and a flow acting on this metric space. Flow is invertible, and an invariant measure, mu. So one can define stable and unstable leaves. We say that x and y belong to the same stable leaf if under the flow, x and y get closer and closer together. And similarly, we say that x and y belong to the same unstable leaf if under backward iteration, backward flow, the points x and y get closer and closer together. So in general, the leaves may not be manifolds, but who cares? Now, the Hopf argument says the following. Suppose you can show that every L2 function, which is invariant under the flow and constant along the leaves of the stable and unstable foliations, if you can show that every such function which satisfies those properties is constant, then the flow GS is ergodic. So this gives a very convenient way of showing ergodicity. Now, mixing is a stronger condition, and Martin Babillot showed that so this time, you're not allowed to use the flow. You are allowed to use only the stable and unstable foliations. If you can show that any function which is constant along the leaves of both of those foliations is constant, then you have mixing. So this is a very beautiful result. And if you want to read the proof, there is a paper by Yves Coudin. It's only 4 pages long. So all I want to say is that this theorem is not only simple, but it saves you a lot of trouble, which I will not explain. But this theorem applies when other things do not. It's a truly fantastic result. When she proved this theorem, the universe changed. That's how amazing this theorem is. She died young. So, okay, before I explain this, let me make a picture to illustrate what's going on. So, to illustrate Babillot's theorem, let's look at the cat map. This is the Arnold cat map. You have seen it before. It acts on R2 mod Z2. In this case, the stable foliation looks like this. It's a bunch of lines. The unstable foliation looks like this. It's also a bunch of lines. And for any 2 points, X and Y, in the torus, they can be joined by a path which travels along stable and unstable leaves. So this picture at once shows that this map is mixing. No, I don't know what the light is, and it is not super important. Thank you, Kant. Long light, you want it? Okay, never mind. So this is the picture. So basically, this theorem says that if the stable and unstable foliations are sufficiently rich, then you have mixing. And what I did is I worked out the stable and unstable foliations in the case which I have been discussing. There are some theorems, not important, but I want to mention they involve rescaling limits. And here in this slide, I want to say the following. If you have a generic dynamical system, you expect that some rescaling limits are different. And in this case, I say that rescaling limits are not aligned. Other authors use the term non-local integrability, which sounds stupid to my ears. But yes, so this is combined with what's written here, one gets mixing. Now, to conclude this talk, I want to briefly mention Neil Dobbs, because he is the hero of this talk. So remember when I said that mixing implies orbit counting? I lied. Mixing implies orbit counting of good preimages. Preimages which are UAL in a quantitative way. So we have to estimate the number of bad preimages. And to do this, we need a lower bound on this Radon-Nikodym derivative. For general dynamical systems, one has to include this as an extra axiom. But what Neil Dobbs proved, that for rational maps, satisfying the axioms A1 and A2, this is automatic. So this spared me the need to include extra axioms. And